Yesterday we did an example where we were just looking at the properties of trig functions, and I said that it was in preparation to sketch. So today what we're doing is sketching. When we did the example that was just the properties yesterday, we did a first derivative chart and a second derivative chart, and that was because it asked for critical points that were classified as well as the intervals of increase and decrease, and then also the points of inflection and intervals of concavity. But when you read these instructions, you'll notice, hopefully, that it says complete a fully labeled sketch of the function below showing all intercepts, critical points, points of inflection, and intervals of concavity. It does not say intervals of increase and decrease. This means we only need to do a second derivative chart. We don't need to do a first derivative chart. And doing a first derivative chart would take a lot longer. So we're going to try to do this whole thing with just a second derivative chart. And all that means is we have to know how to classify critical points with the second derivative chart. But we've already done this. We did this in the previous unit when we did some sketching. So again, I really like to think about how I organize my solutions for sketching, because there's a lot going on and you want to make sure you hit all your bases. And having a habit of how you do things and organize your solution will make it easier to read, and having that habit will make it a little bit faster for you to do, and it'll make sure you don't miss things. Okay, so you may decide exactly what step you do first. I'm going to take this y equals 2 cos x minus sine 2x, and I am going to get it ready to solve, setting it equal to 0 to find the intercepts, okay? And then I'm going to take the first derivative and do the same thing for it, and then the second derivative and do the same thing for it. So I have all my forms. That's the first step that I like to go through. So I have a cos x and a sine 2x, and something we've talked a lot about in MHF and so far a little bit in this unit at least is generally speaking, if we have different angles, we're probably not going to be able to solve it. So we're going to have to do some kind of a swap out. Okay, so this is going to become y equals 2 cos x minus 2 sine x cos x. And I would encourage you, we don't have time to redo all of these things and go over it in detail, so I would encourage you to look back if you really have to at MHF, or ask if you have to, and we can go over it more carefully, but the different strategies for solving, okay? The different kinds of trig equations that we might have, and the different strategies that we might use, different kinds of swap outs that we might use, right? We might have to do a Pythagorean theorem swap out if it's a cos squared x and we're trying to turn it into sine, or a double angle swap out, which we have seen a little bit of already, right? So there's all the different kinds that you might have to see. And then you got to know how to factor it. There's different kinds of factoring. And we've seen turning it into a quadratic and using the quadratic formula. This is a different one. This one is a common factor. So I can common factor out a 2, and I can common factor out a cos x out of each of these terms, right? And so that's what I'm going to do. So I end up with 1 minus sine x, and that's good. That one's set up, ready to go. So now I'm going to take the first derivative. And again, we have 3 forms, but the second 2 forms both would have product rule, and generally that's what happens. So we like to use that first line is going to be the easiest one to take the derivative of. Derivative of cos is negative sine. The angle derivative of x is just 1. So this first part just becomes negative 2 sine x. These questions are long enough as it is that the faster you can take their derivative without a lot of work and having to kind of rewrite it before you start doing other stuff with it, the better off you're going to be. So the next one, derivative of sine is cosine, but I'm also going to be taking the derivative of the angle, and the angle is 2x. So the derivative of that is 2. So this becomes minus 2 cos 2x. And that's what I'm talking about. Being able to write that in one step, already kind of written in the right way that we like it, is useful. Okay, now I am going to factor out a -2. We wouldn't necessarily know that this is the right thing to do, but turns out we're going to end up doing it anyway. If we didn't do it now, we'd end up doing it later. Okay, and I get sine x minus cos 2x. And once again, I have um, a single angle and a double angle, and I also have a sine and a cos. So I generally want them to be both sine or both cos. This situation was a little bit different where I ended up with the common factor. It's not going to be a common factor in this one. So what I want to do is turn this into, whoops, that should be a plus because I factored out the negative. Turn cos 2x into 1 minus 2 sine squared x. So let me go ahead and do that. And the reason is now I have everything in terms of sine and have all single angles. And now I'm just going to sort of fix what I have inside the brackets here. And in fact, this negative is in front of my squared term. I don't want it there. So I'm going to factor it out, and it's going to cancel with that negative. So I hope you can follow this. I end up with 2 sine squared x minus sine x minus 1. So notice how the negative is now gone, okay? And whoops, 2's gone now apparently as well. This negative is also gone. And then these both changed signs, right, from what they were because I factored a negative out of the bracket, and now I've got this in that trinomial form that I want it to be in order to be able to solve it as a trinomial later on. Okay, so that's the first derivative done. Now I'm going to go to the second derivative because we have to do intervals of concavity and points of inflection. And again, I'm going to start with this first line. Okay, and whoops. And so derivative of sine x is cos x. And so it's -2 because it was already -2. But derivative of sine x is positive cos x, so the sign doesn't change. The derivative of cos x is negative sine. And again, I'm going to be doing multiplying by the derivative of the angle, which is 2x, and the derivative of that is 2. So this is going to end up being positive because when I take the derivative of cos, I get negative sine, and that is going to turn that negative back into a positive, plus 4 sine 2x. So it was 2 times 2 to get the 4. Angle stays the same, and that's my second derivative. Once again, I can factor out a 2. I can factor out a -2 or a 2. I'm just going to factor out a 2, and I'm going to rearrange this a little bit. So I end up with 2 sine 2x. This is really just preference stuff. You don't have to do it in this exact way. There's not necessarily a particular reason that I'm doing it this way. I just like to have the negative there, so I'm subtracting instead of adding a negative. Okay, and I'm going to do the same thing we did in the first step, and I'm going to do a swap out for the sine 2x. And this sine 2x is 2 sine x cos x, and 2 times 2 gives me the 4, so I multiply by that 2. And so I get 4 sine x cos x minus cos x y prime, double prime, sorry. Factoring out the cos x again is 2 cos x and then 4 sine x minus 1. And that's the second derivative cleaned up and fully factored, ready to solve. Now I'm just going to stop here and take a break for a minute because this is a long process. And throughout this process of a sketch like this, there's a lot of things that happen, right? We have to just think about the sketch. And sketches alone are a lot of work. Doing the intercepts and getting them mixed up with something else. How do I like asymptotes and end behavior? Well, these don't really have that, but it might be something that's on your mind. and all the different things that you have to think of when you're just doing any kind of a sketch. On top of that, we have to make sure we take the derivatives properly. We have to be able to clean them up properly. We have to remember how to solve a trig equation because we're going to do that several times. We have to remember angles and standard position for trig stuff. So there's a lot going on here. And it will be important, I think, for you to make sure it's clear in your head if you're confused about something or you're not confident about something or you're unsure or whatever it is, or you feel like you're getting lost, that you're thinking about what it is that's causing you to be lost. Did I just go too fast taking those derivatives? Did I go too fast with the cleaning them up and factoring? And when you're reflecting on that, you may be able to narrow it down to one or two things that you're not as confident about or you felt like you kind of missed, and but everything else you're okay with. And that to me is a confidence booster that, wait a minute, I feel lost, but really it's just this one thing or these two things that I feel like I'm not quite getting. So now I can focus my efforts in those areas to pick up on those things. And if that's the case, go and look back at um, the solving and stuff and the cleaning stuff up that we did when we did it more slowly. Even if you have to go back and look at MHF notes or videos from MHF to see that happen more slowly, or just watch this video, watch that little bit a few times and sort of pause to think about what I did and make sure that you can get it. Because this is something we've already done. This is an MHF skill. That's why I am going through it quickly, but I do realize it's been a long time since we've done it. But it's an MHF skill, so I'm not reteaching the whole thing as clearly necessarily, obviously, as we would have when we were first learning it. But I do recognize that it might be something that people kind of missed. So like I said, I would encourage you to rewatch this video and pause so that you can keep up with it, or look back at other examples of this sort of thing, or ask. And we can go over it more slowly. We'll pick one and we'll make sure that we understand it, and that's not what's tripping you up, right? But in a process like this that has so many steps, it really is super important that you figure out for yourself where it is that you feel like you're losing your way, so to speak. Okay, so that's always my first step, getting all three versions ready to be solved. The original formula, the first derivative, and the second derivative, getting them all done. Because now when I do the rest, I can just come up here and pick the version that I need when I need it. Sometimes I'm going to use this version because it might be easier to program into my calculator. In fact, when you've got all this done, you might just go ahead and do that. If you have a calculator, which most people should, that has more than one, in this case, you would need three variables. I could program the first one with variable A, the second one with variable B, and the third one with variable C, or obviously you could use whatever variable you like. You could get them all programmed in now, or you could do them as needed. Obviously, again, that's up to you. But that's one thing where you're going to pick which version you want to program. I think the first version of each of these is probably a little bit quicker to program into your calculator than worrying about brackets and that sort of thing. So generally, I'm probably going to use that top line when I have to solve for y values, um, or do testing on my calculator. I'm going to use that top line. But to solve, I'm always using that last line, because that was the whole point of doing that, is that I got it into a factored form so that I could solve. Okay, so now I'm going to go ahead and start with intercepts. And how do I find the y-intercept? There's no magic here. I'm just punching it into my calculator, making sure that I'm in radians. And on this calculator, I really don't know if I am. It's the one thing that it kind of lacks. So I'm just going to make sure that I'm in radians. And I'm going to go 2 cos 0. In fact, I could do this in my head and it would be faster. Minus, now that I think about it, minus sine of 2 times 0, but I'm showing you what it looks like on the calculator. You're literally punching it in, and that's going to give me 2, isn't it? Because cos of 0 is 0. And sorry, cos of 0 is 1, and multiply that by 2 gives me the 2, and sine of 0, because 2 times 0 is 0, sine of 0 is 0, so this is 2 minus 0, which is 2. So I could have actually maybe done that faster in my head, but you know what? Sometimes you might not. It might almost take you longer to decide whether or not you can solve it. But if it's a 0, the y-intercept, sometimes that is something that we can solve quickly. Okay, and then the x-intercepts, well, how am I going to solve them? Well, they're going to be when 2 cos x times 1 minus sine x equals 0, right? So I took this form and I set it equal to 0, and that's when 2 cos x equals 0 and 1 minus sine x equals 0. And these are both going to end up being questions that I can solve exact value. And when you can do exact value, absolutely you do exact value. And both of these are going to be with the graph. So hopefully this is the kind of thing that we haven't done as much of in a long time, and this is where you do want to be efficient and at doing this so that you don't waste too much time and that you're using the right way of solving. And trig is just a little bit trickier that way. So this is 2 cos x equals 0 is when cos x equals 0, and cos x equals 0, again, using the graph at pi by 2 and 3 pi by 2. Okay, and if 1 minus sine x equals 0, I move the 1 over, it becomes negative, and then I flip the sign on both sides. That's when sine x is equal to 1. And that's sine x is equal to 1 when x equals pi by 2. So interesting that pi by 2 came up with both. In both answers. Doesn't really mean anything. It means less work later on because instead of 3 answers that I'm going to have to do testing for, I only have 2. Okay. I'm just going to make a note here. There's no asymptotes. It didn't even say in the, whoops, no asymptotes. It didn't say in the question, I don't think, to do asymptotes because there aren't any. So it doesn't say to do asymptotes. You don't have to say that, but it's a habit for me. So I do always think about asymptotes after I've done the intercepts. So I'm including it there for that reason. But you don't have to necessarily say that, okay? Now I'm going to go to critical points. So critical values are when y prime equals 0 or does not exist. Y prime exists for all x. Okay, and y prime equals 0 when the first derivative is equal to 0. So that's 2 times 2 sine squared x minus sine x minus 1 equals 0. And for this one, b squared minus 4ac is equal to 9. So definitely has solutions, and in fact, this is factorable. Okay, so very quickly, it would be the same as 2a squared minus a minus 1. That's what we would be factoring. Okay, and it factors 2 sine x plus 1 times sine x minus 1 is equal to 0. Okay, so therefore, I've got sine x equals negative a half and sine x equals 1. If sine x equals 1, then x is pi by 2. We already did that one, in fact. We did it right there. Interesting. And let's see, sine x is negative a half. That means x related. It's pi by 6. And this is where we do the whole cast thing. It's sine and it's positive, so it is the bottom 2 quadrants, quadrant 3 and quadrant 4, which means x is 7 pi by 6 and 11 pi by 6. Okay, so I've got 3 solutions for that. It can be useful. In fact, you kind of have to. It's more than useful. It's basically necessary to have the decimal values, and you can write them down now or you can write them down later. But we're going to need them because we're going to need to know where these are compared to just other values that we come up with. Okay, so it's a good idea to write out the um, the decimal version of all of these different fractions. Okay, and I didn't do it for these ones, so I'll do it later. Okay, I don't think I have enough space to do the POIs over there, so I'm going to do them right here. So we have, whoops, possible POIs, PPOI. Remember, sometimes we find a place where the second derivative is equal to 0 and it's not a POI, it's just nothing. That happens. So we call them possible POIs when y prime equals 0 or does not exist. Okay, and y prime exists for all x, y double prime, sorry, exists for all x. So where is y double prime equal to 0? So I'm going to use my second derivative, which is going to be that version right there. So that is when 2 cos x times 4 sine x minus 1 equals 0. So that is when 2 cos x equals 0. Again, using the graph. And when when sine x equals 1/4, right? When 4 sine x minus 1 is equal to 0 is when sine x equals 1/4. That is our first example in this question that's not a special triangle or a graph question that we can do exact value of. So we are using the calculator and doing shift sine of 1/4. Okay, and I get 0.2527. And I'm going to use that exact value to come up. Again, this is positive, so in this case, for cast, I'm doing quadrant 1 and quadrant 2. And I really only need, probably only really even one decimal place, but I'm going to keep 2 for now. So 0.25 and 2.89. That's really all I need because it's just for graphing. I don't need 4 decimal places. That's not the point of any of this, right? So to get the 2.89, I did pi minus x related because I went to quadrant 2. All right, where are we at? I think we kind of have almost everything done of this stuff. We have to do our chart. Everything else is done, but I want to hold up here for a second because if you're watching, something very interesting happened here. Take a look at this. Pi by 2. Pi by 2. Pi by 2. And pi by 2 here. It happened twice for the x-intercept. We have a critical point at pi by 2. And we also possibly have a point of inflection at pi by 2. There is a lot going on at pi by 2, and that is interesting. And that's going to come out, and we're going to figure out what that means after we do our second derivative chart, which we're about to do. And then when we start to graph it and we start to put things together and make sense of all of this, we're going to have to figure out what's happening there. But it makes sense when we think about it, what's happening, especially if we have a good grasp of the nature of different critical points. Okay, so I'm starting with x. And remember, my domain that I'm graphing this on was 0 to 2 pi. So I don't go past 0 because that's what I also solved on. All 3 of these, the second derivative equal to 0, the first derivative equal to 0. I didn't mention this, and to find the x-intercepts, the original function equal to 0, I only solved from 0 to 2 pi. We know these have infinite solutions. We're used to solving from 0 to 2 pi, but these have infinite solutions. So that's why we have an interval that we solve on and an interval that we graph on. And that means there are more solutions that are less than 0, but I don't know exactly where they are. And so I can't go past 0. I can't go to the left of 0 because I would be going into eventually be going into a different interval. So I start at the beginning, less than or equal to x, less than. What is my first of the 4 solutions that I have here for possible points of inflection? Well, pi by 2, where did I do that? I did that somewhere, is 1.57. 3 pi by 2, I haven't done yet. Let's do that right now. 3 pi divided by 2. So that is 4.7. Okay, so I'm going to put that down, approximately 4.7 for 3 pi by 2. And then I've got 0.25 and 2.89. And so I could actually think about these as quadrant angles as well, I suppose, and figure out which way, because I know what quadrants these came from. This was a quadrant 1, this was a quadrant 2. So it's going to go quadrant 1, then it's going to go pi by 2, then it's going to go quadrant 2, then it's going to go 3 pi by 2 because that's between quadrants 3 and 4. So there's different ways that you could do this, but the decimals maybe is the fastest. We're going to want the decimals later anyway. So our first possible POI is 0.25, okay, and then 0.25, and then 0.25 less than x less than pi by 2. Now, I'll talk about this briefly. It's not something you get hung up on. It doesn't really necessarily matter. I included that because it is part of the interval. So I should include it somewhere. Normally, we don't include it because we're going up to that point, but we don't want to include that point. But because 0 wasn't a number that came up in any of these solutions, there's nothing happening at 0. There isn't a critical value or a point of inflection there. So it's just the end of the interval. So I can just use it, I can just have it that way, and I'm including it because it is part of my graph. But I don't ever include any of the other points, right? We don't include the other points, that's for sure. Okay, so pi by 2, and then pi by 2 less than x less than 2.89. And then 2.89, boy, like I said the other day, these trig functions can have a lot of interesting things going on, and that's sometimes why we cut them back. And sometimes we don't go all the way to 2 pi. Okay, and then 3 pi by 2 less than x less than or equal to 2 pi. Just barely fit it on the page. Okay, and then y double prime and y. Okay, so at 0.25 it's equal to 0, at pi by 2 it's equal to 0, at 2.89 it's equal to 0, at 3 pi by 2 it's equal to 0 because there were 4 solutions for where the second derivative was equal to 0. There are the 4. Now I am picking values, plugging them in to the second derivative and determining if they are positive or negative. So my second derivative is negative 2 cos x plus 4 sine 2x. So negative 2 cos alpha x plus 4 sine, I'm not going to do all of these, bracket, whoops, I already did bracket, 4 sine bracket 2x equals negative 2. It probably thinks that x is equal to 0 or something like that. And now I'm going to store, let's say 0.1, because that's between 0 and 0.25. shift store x up equals, so negative. Okay, so it's negative in that one, and I'm not gonna do all the rest of these. It's positive in this one. Here's another reason why having the decimals is useful, because you're probably punching in decimals. So what is pi by 2 again? Where do we have that? 1.57. So between 0.25 and 1.57, we'll do one more here, is 1. So that one's positive. Okay, so it changed, which means this is a POI, because this was concave down because the second derivative was negative, and this was concave up. It changed from concave down to concave up, so it's a point of inflection. This one ends up being negative, this one ends up being positive, this one ends up being negative. So in fact, all of these end up being points of inflection. So this is a POI, this is a POI, and this is a POI. Okay. And now we have to find our critical values and slot them in. Okay. And my critical values are 7 pi by 6, which is 3.7. So that's going to be in this range. Okay, 7. In fact, I'm going to have one in here. I'm just going to put a little mark. I'm going to have one in there. I'm going to have one in here. That's where 11 pi by 6 is. And then I am also going to have one at this point, because remember, that's where there was a whole bunch of stuff happening at pi by 2. Okay. So when I am concave down, that looks like this. That is a turning point with a max, and that's at 11, whoops, pi by 6, and punching this into the original equation, 2.6. This one is concave up, so that's a turning point with a minimum. And that is at 7 pi by 6 and negative 2.6. I skipped this one. This is a POI. It came up before, but it was an x-intercept, so that's not anything we have to worry about. It's just an x-intercept. So 3 pi by 2 and 0. We already know that. I don't have to punch that into the calculator. If I did, I would just get 0. If I used a rounded version, I would get close to 0, and that might mix me up. So we want to make sure we're putting in the actual value there. This POI is 2.89 and negative 1.46. This one is 0.25 and 1.46. So we can see some symmetry sort of happening there in some different areas. And then this one is pi by 2. And again, it was an x-intercept, so 0. Okay, so I've got A, B, C, D, E, and F. And the last thing I have to do, this is kind of new, I did mention it, I believe, but we weren't really doing a full sketch, is you have to find the start and the end. So the start, okay, this is part of this process. Maybe it should even say it up in the instructions, but it's just part of the process, is that we want to know the y value. We know the x value of the start, it starts at 0, and we know the x value of the end, it ends at 2 pi. We want to know what those y values are. So this is 2, and this is also 2. Okay, start and ends at 2. Starts and ends at 2, which is, again, just kind of a fluke. But it could be that this is one cycle of this graph, and that's why it starts and ends at 2. In fact, I think maybe it is, but that's definitely not always going to happen. Okay, so I think I've got everything. Let's just go back and take a look. I've got my intercepts. I did all of the derivative stuff that I needed in order to find critical values and in order to find possible points of inflection. and then I used a second derivative chart to not only determine if all of those points are points of inflection, but also to classify my critical value or my critical points, right? All right. Okay, we got that part done. Um, I've sort of mentioned this before. It's maybe a little bit strange, but it's actually easiest to mark off um, like whole numbers or integer numbers for these. So I'm going to go 1, 2, 3, and 1, -1, -2, -3. And I need to split this up into 6 because I'm going to 2 pi. So if I put 6 right about here, then I go to about half of that. That's going to be 3. And then I got to break that up into thirds. You could use a ruler for this, of course. That wasn't great, was it? That was better. And then, not bad. So that's 2, 4, and 6. Okay, so I've kind of got that split up like that because I've also got all the decimal values. Okay, so I'm starting at 2, and that's in a concave down region. My first thing that's happening is at 0.25, so it's happening right around here somewhere. I'm not going to draw that point yet. I'm drawing it just to show you. Okay, that's a point of inflection. So again, we've talked about this. It can be, unless it's a really obvious point of inflection, it can be difficult to draw it in exactly the right place or know exactly where it is. So do your best. The next thing that's happening is at pi by 2, and pi by 2 is 1.57. So it's around the middle of that section, and it has an x-intercept, and it has a horizontal tangent line, which turns out to be a, oh, we didn't actually mark that. We didn't talk about that. I'll talk about that now, and then maybe I'll go back and mention it later. Um, it's also a POI. So watch what happens here. So this is concave down to concave up. And then it's going to be a horizontal tangent line right around the middle of that. Okay. I changed from concave down to concave up right about there. So that was my first point. But then I've got this spot here where I have a horizontal tangent line. And notice that this is concave up and this is this region. So it should be concave up. And now it's changing to concave down. But it was also a horizontal tangent line. Well, if I'm going to change from concave up, horizontal tangent line to concave down, that's a cubic twist, right? And if I had checked the first derivative chart, I would have used increasing and decreasing to show that because we know how to do that with increasing and decreasing. But this is what it looks like with a second derivative chart. If it changes, if it's a critical point and it changes from concave up to concave down or concave down to concave up, then it has to be a twist. So I'm coming in and I'm twisting to change to concave up. Okay, I'm going to do that a little bit more gentle, so like that. Um, there we go, like that. What's next? I'm always kind of looking ahead at what's next. Next is point C, which is a POI. So it's concave, I'm concave down right now, and that's at 2.89, so not quite 3. So I'm at concave down. Whoops, that wasn't very good. To concave up before I get to 3. And then I have a turning point with a minimum at -2.6. So not quite at -3, but more than -2. And it is at 7 pi by 6, which is 3.7. So it is close. Whoops. So I might have to redo that again. It's somewhere going to be somewhere right around here. Okay, this is point D. Yep, right about there. So that's what I'm aiming for this time. And then I have my next interesting point, point E, is at 3 pi by 2, and 3 pi by 2 is 4.7, and it's also an x-intercept. So it's right about here, something like that. Okay, and so I'm concave down, whoops, concave down, concave down, concave down, concave down, and then changing to concave up. And I'm going to point F, which is a turning point with a max, at 11 pi by 6, which is 5.8, and at 2.6, so somewhere right around there. And then I am finishing at 2 and at 6.28, which is 2 pi. So right around there, let's say. And that region is still concave down, as I can see right there. Okay, let me go back and mark these points a little bit better and make sure that I have them all. So I had A there, B. Oh, I got a C in here that's missing, right about there. C, D, E, F. Okay. And I think that's about it. I mean, I've labeled my points. I've labeled them A, B, C, D, which corresponds to these values over here. So I don't have to put the 3 pi by 2 and pi by 2s on there because I think that's pretty clear. Labeled my scale. I got everything done and not bad. You can see how much stuff is going on in questions like these. Just a lot of stuff going on. And there are a lot of things to think about because it's trigonometry. The solving is trickier. The factoring is trickier. We end up with a lot of things that we have to check, and we got to be careful if we're checking the second derivative or plugging into the original equation or what exactly we're doing. Okay. But anyway, that is graphing trig functions. Again, I encourage you to really reflect on if you're feeling overwhelmed or you're feeling like you're not there's something important that you're missing. Really reflect on what exactly it is, because it's probably one or two specific things, and that might cause the whole question to fall apart, but it gives you something to focus your efforts on. And once that part clicks for you, hopefully you'll be able to do the rest of it as well. Okay. The practice is just 3 sketches. There's the 3. Important to note that for the second one, it gives you the x-intercept because you wouldn't be able to solve for it otherwise. All of them are from 0 to 2 pi. Okay, and otherwise you're doing the same thing as the example that we just did: intervals of concavity, intercepts, critical points, and points of inflection. Okay, good luck.